Hi everyone, this is the review session for midterm number 4, I guess the final in some respects. As has been our tradition, it's 8 to 8:30, but instead of Monday, Wednesday, Friday, it'll be the Friday of week 14, which is the first Friday after you come back from Thanksgiving, or don't come back as the case may be, and then the Monday and Wednesday of the week following. So be aware of that. It's updated in the syllabus, so you should be aware of that. Don't turn up at the wrong time. Again, if you have problems in submitting, then just send a copy of what you have. You're working as soon as you can, certainly within 10 minutes of finishing, and then that would be not a problem. The topics for the course, the final, are pipes and pipe networks, which is really 11.3, but 11 would be safe. External flows, which is week 12, and then open channel flows of week 13. And in terms of the individual components, the Friday midterm is on pipe networks, which is really 11.3. The Monday following that is external flows, and then the final is on the Wednesday, which is uniform flows. Yeah, I guess out of all the material in chapter 13, uniform flows is probably the most straightforward. And so this is the material for the scheduled exam, and I'll just go quickly through it. Week 11 material relies on the energy equation, as you know. If I can write it properly. And you know that if you look at the behavior from flowing from one tank to another, in terms of this response, big tanks flowing from one to another in this particular case, then the behavior that you would expect to get would be some drop in head between those locations, which we can call, for one pipe anyway, H sub L. And the energy equation defining that is depending on where you want to write your expressions, and you've seen this also many times before, that pressure head plus elevation head plus velocity head plus any pump components has to equal the pressure head on the downstream. We have to write it correctly between upstream and downstream because of the irreversible losses in the system. And we have both the sum of major losses and the sum of minor losses. Individually, I guess these we know are things like the head loss of one component is equal to the friction factor, length over diameter times the velocity squared over 2g in that pipe. And likewise for fitting losses, the head losses would be of the order of some loss coefficient times v squared over 2g. And deliberately, these are written without numbers attached to them because they refer to the individual fitting or component that we're interested in. In terms of what those represent, we know from the Moody charts that Reynolds number, which is a velocity, a characteristic length, and a density divided by viscosity. This is usually a hydraulic diameter, and a Euler number, or a friction factor, or a coefficient of drag, or a coefficient of lift, or a Manning's coefficient are all the terms on the vertical axis, and those are divided between laminar and turbulent behavior with different characteristics. In the laminar regime, the friction factor is a function of Reynolds number, which means that the behavior in terms of head loss is proportional to, or viscosity, and in the turbulent regime, delta HL is proportional to density. And so we, likewise, the solutions we get here are that it's also proportional to velocity, and it's also proportional to velocity squared. So different relationships within each of these areas. So in this particular area, for laminar, then friction factor is a function of Reynolds number. In the turbulent regime, it's not a function of Reynolds number and is constant with Reynolds number. If we're looking at behaviors of individual tanks with multiple pipes connecting them, then we know that for connections, we have two different behaviors. We have in series, we have, say, pipes that are joined in individual components between upstream and downstream, in this particular case. And in parallel, we have pipes which join two tanks, which might be of different diameters, for example. I'm trying to join these by tanks for good measure. You get the picture anyway. Suppose we could use different colors to represent the head between upstream and downstream. And so in this particular case, this would be the head loss. And so if we have pipes 1 and 2, the different requirements are that the total head loss in this system is equal to head loss 1 plus head loss 2. And conversely, the total flux is equal to the same amount in each component. So the flow rate in pipes 1 and 2 have to be the same in this particular case. And I suppose the converse is true here, is that delta HL is equal to, again, for 1 and for 2, because they both discharge into the same tank from one to another, delta HL1 is equal to delta HL2. I guess it's really no delta involved. But in this particular case, Q total is equal to Q1 plus Q2. Q2. And so, this would just be a summation in each of these. So delta HL is equal to the sum of HLI. And in this case, Q is equal to the sum of QI. So those are the requirements for multiple flow in multiple pipes in terms of systems. In terms of external flows, which we also dealt with in week 12, this all starts to repeat itself. I suppose we define behavior on any structure. Whoops. So if we have that's not bad, is it? If we have forces acting downwards, which would be mass times gravity, and we have buoyant force acting upwards, and we also have a drag force, which we've always called squiggly, what I call squiggly d. Then we just use Newton's second law, and that is the sum of the forces are equal to mass times acceleration. Typically this is equal to 0. Not always, but typically. And it's just a force balance. And the behaviors of those, in each case, the coefficient of drag is equal to some drag force divided by convention. There's a half in there, rho v squared times area. You recall that if we lump these two terms together, this becomes a pressure, which we can think of as this as being an Euler number, and the coefficient of lift is equal to some lift force divided again by half density of the fluid that's flowing around it times the velocity squared times the area. So the area depends on what kind of system it is. So typically you'd be given what the cross-sectional area is. So if it's an airfoil, it would be the top area of, say, of the wing. If it's drag, it would be the planiform area that's forcing its way through the fluid. So the area, characteristic area or characteristic dimension matters. And it comes back to a Moody-like plot, once again, of Reynolds number is equal to a density, a velocity, and a length dimension by viscosity. And again, it divides between laminar and turbulent, and this is now a coefficient of drag or a coefficient of lift, which is also really an Euler number. And we have these two regimes. If you look at the behavior of a sphere, then it ends up being something like coefficient of drag is equal to 24 divided by Reynolds number. And once you get into the turbulent regime, you may get a few little ripples in this, but basically it's the same as before, and that is that the coefficient of drag is constant at all Reynolds numbers beyond the threshold of laminar to turbulent. And so again, the coefficient of drag, and therefore the drag force. Whoa, what's that? Coefficient of drag and drag force is proportional to viscosity, because it's proportional to Reynolds number in this case, inversely proportional, I guess. And the drag force also is proportional to viscosity. And in this regime, the coefficient of drag is proportional to density only, and the drag force is proportional to density. And really the reasons for that are, I'm not sure whether we went through it in this particular class or whether it was in the recordings. If you look at flow, in this case, past someone wearing one of those funky bike racing helmets, if you look at the flow regime that occurs past this, in a laminar regime, then basically what it's doing is it's generating shear stress along this boundary, and this shear stress is a function of viscosity. If you're in this regime here, then typically, just as in the case of the truck being dragged behind the aircraft, the stagnation on this boundary is the bulk of the force that's applied, and that's proportional to the momentum that is destroyed on that face, which is proportional to density. And so the different dependencies you get in these different regions require that you end up with, in your force balance, you end up with different dependencies. This being something that gives you velocity directly, and you end up with a v squared term that you have to square root in this regime. So potentially you're solving either for a drag force or a lift force that's applied. And if you know what that force is, then the one unknown in this expression is the magnitude of the velocity term. And so when you rearrange for velocity, in the laminar regime, typically you get a function which is a function of velocity to the power 1. And typically in the turbulent regime, you get a function which is velocity squared, which you have to square root to be able to get the actual velocity out of it. Okay, what's this? Let's get rid of this. I don't know what that is. I don't know. So it's something strange. Well, let's go beyond that and get back into this. And so the final item is for open channel flows. The material that we covered was for gradually varying flows, rapidly varying flows, and uniform flows. And so I've already said that my gift to you is the fact that it'll be uniform flows, which are by far the most straightforward of all the things we talked about in terms of flow regimes. And it requires the Manning's formula. And that is that the flow velocity, the average flow velocity, averaged over the cross-section, is equal to kappa divided by Manning coefficient and multiplied by the hydraulic radius to the power 2/3 times the bed slope to the power half. So hydraulic radius is just equal to, it's an equivalent to an hydraulic diameter, which is an area divided by the perimeter. And so if you have a flow cross-section which is filled to some height that you have here, the area is clearly this cross-sectional area, and the perimeter is equal to the wetted perimeter, which clearly doesn't include the top surface, because it's not in friction with frictional contact with anything. If we want to calculate the volumetric flow rate, it's equal to the velocity, average velocity, multiplied by the cross-sectional area flow, same as this. And that allows you to be able to calculate what the volumetric discharge on one of these sections is. So that's about it. That's it. So the full suite of equations that we talked about this, you shouldn't need anything more than that. And so if you have that and the understanding from the previous part of this class, I think you should be just fine with this test. Okay, good luck. Thanks.